Now example 5.11, slowing down of neutrons. In a nuclear reactor, a neutron of high speed, typically 10 raised to 7 meter per second, must be slowed to 10 raised to 3 meter per second so that it can have a high probability of interacting with isotope and causing it to fusion. So up to this one, the understanding related to the fission process that is given to you. In fission process, the neutrons that should be with speed 10 raised to 3 meter per second. Then successful fission is possible. Now the example that is starting from this point. So that a neutron can lose most of its kinetic energy in an elastic collision with a light nuclei like deuterium or carbon, which has a mass of only a few times the neutron mass. The material making up the light nuclei, usually heavy water D2O or graphite, these are known as moderators. Again, that is the information, right? So moderators slow down the neutrons. Okay. Now see, initial kinetic energy of neutron, suppose, that is K1I, that is half M1 V1I square. Okay. So final kinetic energy that we can write K1F, that is half M1 V1F square. So final kinetic energy, that is after collision of neutron with deuterium. Then after collision, suppose neutron is moving with velocity v1f. So we can write the velocity after collision for the neutron, that is k1f equal to half m1 v1f square. Initially deuterium is stationary. Now due to this collision, some kinetic energy will be lost by neutron and some kinetic energy will be gained by deuterium. Okay. So here first we calculate the kinetic energy after collision. So after collision, what will be the speed of first particle or colliding particle? So v1f equal to m1 minus m2 upon m1 plus m2 into v1i. In previous theory we discussed this thing. Okay. So if we substitute this value of v1f here, then we will get k1f equal to half m1 into, now substitute this entire thing for this v1f. So m1 minus m2 upon m1 plus m2 whole square into v1i square. Okay. Now we have to find the fractional loss of kinetic energy for neutron. So fractional loss, that is final divided by initial. So the fractional kinetic energy lost, F1, that is final divided by initial kinetic energy. That is now final, this equation, initial, that is half m1 v1i square. So here half m1 cancel, this v1i square cancel here. So you will get resultantly m1 minus m2 upon m1 plus m2 whole square. Now this one is the fractional lost in kinetic energy for a neutron. Now here what is the gain in kinetic energy of deuterium? Okay. So if we consider the initial total kinetic energy, that is 100%. So we can say the fractional kinetic energy gained by deuterium, that is F2 equal to 1 minus F1. That is 1 minus F1. Now substitute here value of F1. So that is 1 minus M1 minus M2 upon M1 plus M2 whole square. But here it is written as M1 minus M2 square upon M1 plus M2 square. It is one of the same thing. Now take LCM here. So m1 plus m2 whole square minus m1 minus m2 whole square upon m1 plus m2 whole square. So if we simplify this numerator, we will get this is equal to 4m1 m2 upon m1 plus m2 whole square. Clear? Okay. Now this one is the fractional gain in kinetic energy for deuterium. Clear? Okay. Now see here. If we take F1 that is equal to m1 minus m2 upon m1 plus m2 whole square we derived earlier. Then F2 that is 4m1 m2 upon m1 plus m2 square. Now here for neutron and deuterium, if we take mass of deuterium that is m2, then that is twice m1. That is twice m1. So m2 that is equal to twice m1 if we substitute in these equations. Then we can write F1 that is equal to m1 minus 2m1. m2 is replaced by 2m1 upon m1 plus 2m1 whole square. If you simplify, you will get 1 by 9. Okay, it is 1 by 9. Okay, and now if you take F2 that is 1 minus F1 that is 1 minus 1 upon 9 that is 8 by 9. So here we can say after collision the fractional kinetic energy gained by deuterium that is the maximum one. Clear? So almost 90% of the neutron's energy is transferred to deuterium. Okay.